Now, isotopes can become unstable, or when they are unstable, or they do not make it to the checklist of the rules that we did. Like, for example, lithium-9, which is an unstable isotope of lithium, or AT209, which is also unstable. Based on the rules that we set, these unstable isotopes are more reactive. So they have a tendency to react or to decompose, or what we call as decay. So this process, when isotopes decompose or decay, it's called radioactivity. So there are a few nuclei that are naturally occurring in nature, and that accounts for natural radioactivity. Now, there are a lot more that are made or induced artificially. How did they do this? They bombarded mga stable na nuclei with high energy na particles. And then, the radiation that they give off may be either in the form of beta, or this symbol. The symbol for beta is the Greek letter alpha, and gamma, which is usually Y. Some textbooks would indicate this as small letter B, or small letter A, or small letter G. But in reality, it is beta, alpha, and gamma na symbols, Greek symbols. So beta particles are identical to ang iyang properties are identical to electrons. So most of the time in nuclear reactions na equation, they are symbolized by electron particles. Alpha particles are helium na particles, or helium na nuclei. Helium-4 carrying a +2 na charge because the 2 extra nuclear electrons of the helium atom are missing. So positively charged na helium. And gamma rays, which consist of high energy radiation. Then, the mode of decay. So naturally occurring radioactive na nuclei commonly decompose by a couple of ways. The first one is through alpha particle emission. So an ordinary na helium nucleus, which is helium-4 with a positive charge of +2, is given off. So when a radioactive na isotope, like for example, uranium-238, it is one of the most common radioactive isotopes, would decompose. Mo decay siya. The one predictable, through alpha particle emission, the one predictable na product is the alpha particle, symbolized by a helium-4 particle. And how do you see? How do you get the other product? Dapat balanced ba ya? So on the left side, the total A is 238, and the total Z is 92. But for this one, you have an A of 4 and a Z of 2. So you just subtract it to predict the next product. So you have an A of 4, a Z of 2. So to predict the other product, you just subtract. Dapat balance ba ya? Dapat the A is equal to the A, the Z is equal to the Z. So 238 minus 4 is equal to 234. Z 92 minus 2 is equal to 90. Then, what do you do next? You look at your periodic table, and we know that the identity of a certain na element can be dictated depende unsa ang iyahang atomic number, or yung number of protons, or ang iyahang Z. So you look at Z with 90, or the atomic number 90, and what falls on it. And you can see in your periodic table that it is thorium, or TH. periodic table, it is thorium. And now, just follow the symbol. We have your 2, 3, 4, and 90. So that's how you could predict or how you can get the other product in alpha particle emission. Okay? So that is that is predicting the daughter nucleus in alpha particle emission. So, the alpha particle is by far, it is the most massive, it is the biggest na particle emitted by a radioactive na nuclei. So it has the highest ionizing power or the ability to ionize, turn into ions, ang molecules or ions. Mo-charge siya. Because sa kadako sa size sa alpha particle, they have a difficulty. So maglisod siya og penetrate og cells. They can be easily stopped. So they can be easily stopped by clothes or clothing. It can be easily stopped by skin or even a sheet of paper. Yes, they are very ionizing, but because they are very big, it's easy to block them off. So, mga alpha-emitting na nuclei that are outside the body are relatively safe. So, less danger posed as long as they are outside the body because your clothes, your skin can stop it from ionizing your cells. Mamanang important that radioactivity doesn't penetrate your cells. Okay? But if we inhale or we eat, we ingest or it is injected kanina mga particles, it would be more dangerous because ang cell membrane or the outer covering of individual cells is not capable of stopping alpha particles. So as long as you are protected by your skin or a piece of paper or ang armor nimo is a piece of paper or even your clothes, you are in less danger to alpha particles, alpha particle emission. Then another mode of decay for naturally occurring na nuclei is beta particle emission. So in beta particle emission, it produces an electron or a beta particle. And it is given the symbol because a beta particle, as we discussed, is very close ang yang characteristics to an electron. It is symbolized in nuclear equations as an electron. So of course, 0 ang iyang weight and ang iyang charge is -1. So because A is the total number of neutron and proton, 0 jud na siya. Kaya wala man siya neutron, wala sad siya proton. So this is an example of a beta na emission of cesium. So when cesium decays, it releases a beta particle or an electron, and ang iyahang daughter particle is barium. So let's try the example for the beta emission, which is thorium-234 decays to release through beta particle emission. It decays to protactinium-234. So we know that thorium decays through beta particle emission. How do we determine again? How do we determine the other daughter particle, which is protactinium? So still, you should balance the mass number and the atomic number. So this is A is equal to A, Z is equal to Z. So 2, 3, 4, and 90. And this is 0 and -1. So, in other words, the other daughter particle, if this is X, let's just say this is X, this is unknown. It should carry the mass number of 2, 3, 4, and 90 plus -1. Be careful with the negative symbol. 90 plus -1. Or 90 minus -1, I'm sorry. 90 minus -1. So, this should carry 91. And then we just check using this one, your atomic number through the periodic table. you can predict that it is protactinium 234, the mass number of 91. So for this one, cesium, let's try cesium. That's CS 55137. It decays through. How do we determine it? So we know that it is 13755, and then it's 0, -1. So this should be 137. This should be 56. So So 56, which is, if you check it in the periodic table, that should be barium. Through the periodic table, barium 56 and 137. So if you add the mass number from the product side, it should equate to the mass number sa reactant side, same with the atomic number. Next is the gamma radiation. So for gamma radiation, so for beta particles, by the way, just iyahang further na characteristics is that if you can see from the nuclear equation, same ang mass number sa protactinium as the reactant, which is 234. Same with cesium and barium. Ang iyahang difference lang is ang iyang atomic number, which mo increase of 1. So, in other words, mura ganig mo convert si beta emission from a neutron to a proton. That's why maadan og 1. Why? Because ang nuclei, this usually occurs, class, because the nuclei contains too much neutrons for stability. So it tries to achieve stability by converting that certain neutron into a proton. Then, beta particles are smaller and lighter than alpha particles, so they can penetrate cells more easily. But they have a lower na ionizing power. So a sheet of metal can stop their entry into cells. Even when they are ingested or inhaled, they are still less destructive versus your alpha particles. The last mode of decay for naturally occurring is the gamma radiation. So it consists of high energy na photons. And because gamma emission changes, it doesn't change anything. It doesn't change the mass number. It doesn't change the atomic number. It is ordinarily emitted. Omitted. Dili siya i-write in nuclear equations. Now, because it is small, it has the lowest ionizing power. But it needs several inches of lead or thick cement to block necessary gamma ray penetration. Even if it is less ionizing, because it is so small, it can easily penetrate cell membranes. Need siya og inches of lead and cement. If you take a look at some information about Chernobyl, for example, they use this concept as well. So in this illustration, you can see that the gamma ray has A and Z of 0. 0 A, atomic number, 0 mass number. So, and it is symbolized by a photon. Photon lang siya. And the daughter nucleus is kind of the same with the parent nucleus. It's just more relaxed because ni-release siya og energy. So, it is less excited. Okay? If it is less excited, it is less reactive already. Again, it's for stability man. So, for artificially made na radioactive nuclei, it can decompose by, the first one is positron emission. So, sa man ng positron? A positron is identical to an electron. Same siya og electron, but it has a charge of +1 instead of -1. So here, wala na lang gi-indicate ang charge because it's positive, but that is +1. So, na-convert si neutron into, so a proton is basically converted into sort of a neutron from a K40 into argon na 40. So, ang positron emission is characteristic or happens to nuclei na daghan kaayo og proton for stability. So, it's the opposite. So, ang iyang buhaton is to release or convert that certain proton into a neutron. So, in this example class, for K or potassium 40. So let's try and see. Let's try and predict what is the daughter particle. And saan na to pag-predict, or how do we know that it should be argon? So this is 40. 19. This is 0 and +1. Therefore, to balance this out, it should be 40. And 19 minus 1, that should be 18. So if you look at your periodic table, the element with the atomic number 18 is argon. So using the periodic table, then you can predict your daughter particle. The same with this one for carbon 11 for positron emission. So this is carbon 11. It releases a positron, an electron with a +1 charge. So what would be the daughter particle? So this should be 11 and 6. Dapat the left side, or the right side should also be equal to 11 and 6. So you have 0, this is 1. So this should be 11, and then this should be 5, 6, 11, right? Para balance. So what element has the atomic number of 5? That should be boron. So that is the daughter particle when a carbon 11 would go through positron emission. Another way it could decompose, or artificially made radioactive nuclei could decompose, is through K-electron capture. Now, it is when an electron in the innermost level, or N is equal to 1, diba, na ay energy levels, magkalayo siya, magkasayon siya, mawala, right? In normal na chemical reactions. For this one, the energy level is in N is equal to 1. And the electron there would fall into the nucleus, mabitad siya into the nucleus. Anong gitawag siya og K? Because the name of that energy level is letter K. It goes K, L, M, and so on. That's why it's called K-electron capture. And it is closest to the nucleus, so it is absorbed. So what would happen? So in this example, it is the same concept as a positron emission. Ang mass number would not change, but the atomic number would decrease by 1. So this mode of decay is common with the mga heavy na nuclei because ang N is equal to 1 is closer to the nucleus as well. So here in this example, this is RB RB82, and it would undergo K-electron capture. So this time, ang imuhang electron is in the reactant side already, not in the product side. Kay capture man siya, dili man siya emission class. So, to predict the daughter na particle, it is still the same concept. I-balance gihapon nimo ang mass number, balance gihapon nimo ang atomic number, and then you could predict using the atomic number and check. You could check your periodic table unsay naa na atomic number. This one is for rubidium 82, mass atomic number of 87. So 82 and 37. This time plus 0 plus -1. So, unsay total? 82 and 36. So, to balance, dapat 82 and 36 po sa right side. 82 and 36. Check in the periodic table, unsay na ay 36. It is krypton. So, it should be krypton 82 with an atomic number of 36. So, if the rubidium, if the electron in the innermost na level, energy level of rubidium 37 falls into the nucleus, it captures that electron and it would become krypton 82. So, here is a summary, short summary of the modes of radioactive decay. We have the alpha decay, beta decay, gamma decay, positron emission, and decay electron capture. Again, these are for naturally occurring, and these are for artificial. So, ang ma-emit during alpha is the helium-4 na atom, which has a charge of +2. For beta decay, that is an electron. For gamma decay, photon, negligible. Positron emission, it is a positron, positive electron. K electron capture, walay ma-emit, only ma-absorb. Examples are, and then we have the charges and the penetrating power, how much they could penetrate. Then, let's have an example for promethium with an atomic number of 61. So, promethium is essentially non-existent in nature because it is one of the rarest of the rare earths na elements in the periodic table. So, all of its isotopes are radioactive. So, we are to write a balanced nuclear equation for the decomposition of various isotopes of promethium. So, the first one is promethium-142 by positron emission. So, let's start with the first one. PM-142, and that is positron emission. Okay? So, start with PM, emission man siya. So, that is 142. Check in the periodic table what is the atomic number of promethium, or you could use the 61 already given. A positron is a positive electron with a +1 charge. So let's try and predict the daughter particle. To predict the daughter particle, you have to balance. We have 142 here and 61. The other side, we have 1. So this should be 142 and this should be 60. So to check in the periodic table, ang 60 sa periodic table should be neodymium or ND. So therefore, the daughter particle should be, so this is your balanced na nuclear equation. Next, for letter B, we have promethium-147 by beta emission. So we have it emits a beta particle or an electron. To predict the daughter particle, let's balance. So it should also be equal to 147 and 61 sa other side. We have 0 and -1. So to make this 147, daughter particle should have 147. To make that 61, the daughter particle should have 62. And checking the periodic table, it is samarium or SM. So the daughter particle is samarium-147. This is your answer. Next, we have Promethium 150 by alpha emission. So that's PM 150 and 61 emission. Alpha particle as helium-4. Let's predict. This is 150 and 61. The other side should also equal to 150. So, to make this 150, this should be 146. And to make this 61, this should be 59. Thus, 150 and 61. So, from the periodic table, 59 is PR, or praseodymium. You do not have to memorize all of this. You will be using your periodic table. That's PR 150 and 61. This is the answer. Sorry. This is PR 146 and 59. That is the answer for the sample problem. Let's proceed to bombardment. So more than 1,500 or 1,500 radioactive isotopes have actually been prepared in the laboratory. Ang number of such isotopes per element ranges from 1 to 34. For hydrogen and boron, we have 1. For indium, we have about 34. They are all prepared by bombardment reactions. From the name itself, ang usa ka stable na nucleus, it is converted to the radioactive na isotope or nucleus when it is bombarded by certain particles. And it is bombarded by a certain particle and then it becomes radioactive, which then makes it decay to more stable products. Ginana nila pag-produce ang uban na elements in the periodic table. So one example of a bombarding particle could be a neutron. So it is low energy. It is produced in a fission reactor. A typical example of a reaction for neutron bombardment is the following to the right. So this is the first step. You bombard siya. This is bombardment. Upon bombardment, you are bombarding with a neutron. So still balanced. And bombarding aluminum-27, you could get its radioactive isotope, which is aluminum-28. Now, aluminum-28 is radioactive and it decays by beta emission. So, through beta emission, it can decompose into silicon-28, which is a more stable. Next, this is another example. In the illustration below, you have uranium-235, which is relatively stable. It's bombarded with a neutron. It becomes a radioactive na isotope, which is uranium-236. And uranium-236 then decays into its daughter particles. Another particle used from bombardment is your charged particle. Unsa maning mga charged particle? Charged particles could be an electron or a positron or an alpha particle. And they are accelerated at very high velocity, so they're very fast in using electric or magnetic fields. This way, ang charged particle could get enough energy to bring about a nuclear reaction despite the katong atong gitalk about na repulsion in the components of the atom. So, this illustration is just a way to visualize your bombardment using a charged particle. This time, the charged particle used is the alpha particle with a +2 charge, or it is also it is denoted by the helium-4 na atom. So, gibombard niya and then it creates a new element through decay already. So, the first radioactive isotopes to be made in the laboratory were prepared in 1934 by Irene Curie and her husband Frederick Joliot. So they achieved this by bombarding certain stable isotopes with high energy or accelerated na alpha particles. One example that they did was they bombarded aluminum-27, which is stable, with helium or the high energy na alpha particle. It produced P30. Excuse me. P30 or phosphorus. A phosphorus and a neutron. And then phosphorus is radioactive. It further decayed into silicon. So phosphorus 30 is radioactive. So it, through positron emission, ni-emit siya og positive electron, it created a stable element. So that's silicon. So some na application of bombardment reaction is actually the preparation of the transuranium elements found in your periodic table. So it starts with neptunium, which has, or NP, which has the kanang atomic number of 93. That is in 1940. So a series of elements with atomic numbers greater than uranium. Uranium is 92. Sila ang gisynthesize or gihimo in the laboratory. So much of these work of the transuranium elements are done in the University of California in Berkeley under the direction of Glenn Seaborg. And later by Albert Gorso. And a Russian group in Moscow, in Dubna, led by G.N. Flerov, made significant contributions as well. So, there are also heavy elements from 197 through 212 that are prepared in the late 20th century by a German group led by Peter Ambruster. Most of the nuclei produced have half-lives of microseconds. So mo-decay sila, mo-half ang ilahang mass in microseconds, less than seconds. Experiments reporting the formation of elements 113, element 115, and element 117 have been reported in some journals, and they are identified by the IUPAC already. So in October of 2006 as well, from the Lawrence Livermore National Laboratory, still in California, USA, and together with a nuclear research institute in Russia, they detected element 118, which was before named as ununquadium, but right now it is identified as oganesson in most periodic tables. So how they did it was how they found out that it existed, because gipredict na ba yan gipredict na ba yan ni before when the periodic table was created. So, ang existence ni element 118 was already predicted. So, ang ilahan ng problema is how they synthesize it. So, they synthesized it by colliding, or through the collision of CF249 and Ca48, which produced your OG element number 118 through a release of 3 kabuok na neutron. So these are just some applications. Yun sa nila pag-fill in. How do they synthesize the other elements in the periodic table through bombardment already? So these listed, the synthesis of transuranium elements are listed below. Neutron bombardment is quite effective sa lower na members of this series, mga elements number 93 to 95, just after uranium. But ang yield decreases sharply with the increase in the atomic numbers. So, greater than 96, mo decrease na ang iyahang product yield. So, to better form or effectively form heavier na transuranium elements, it was necessary to bombard appropriate targets with higher positive ions. Thus, you could see that instead of a neutron, they used here helium, they used carbon, nitrogen, and oxygen, or positive ions na siya, thus creating the next in the series of the transuranium elements. So, what are the applications of radioactivity? So it's not all bad, class. I know it when you hear the word radioactive or radioactivity, so much negativity comes to mind because of previous na failures in the field or in the industry. Na yung mga um, um, instances across history that proved it to be so catastrophic. But right now, we have so much application in the industry, in various industries that are helping us day to day without us even knowing it. So the first one is medicine. So radioactive isotopes are commonly used in cancer therapy. That is to eliminate malignant cells after surgery. Ang isotope that is commonly used is cobalt-60. So gamma rays from this source are focused on small areas na they suspect where cancer is. There are certain types of cancers that can be treated internally with some radioactive isotopes. So for example, if a patient is suffering from cancer sa thyroid, um, they would drink a solution of sodium iodide or NaI containing radioactive na iodide ions. And kana na iodine moves preferentially to the thyroid gland, and ang radiation from that iodide ions would destroy ang malignant cells without affecting the rest of the body. Diba? It's so cool and amazing that we found out that something so dangerous could actually help or benefit us. We could use um this advancement in science, in chemistry, for example, to harness its power and to help people lengthen life or improve survivability. So, more commonly, ang radioactive nuclei used for diagnosis are listed in this table. So, we have fluorine for brain scans, sodium, circulatory disorders, phosphorus for detection of eye tumors. Remember, these are isotopes, okay? They are all radioactive. And we have positron emission tomography or PET. I'm sure you have heard of a PET scan. It is a technique used to study mga brain disorders. So patients are given glucose and naay radioactive isotope of fluorine that is attached to it. Now, the fluorine isotope is a positron emitter. So, ang brain then is scanned. I-detect niya asan ng mga positron emission from the radioactive na labeled glucose. So, in this way, ang difference in glucose uptake and the metabolism of patients na normal versus the abnormal na brain scan is seen, and mamap nila asa ang disorder or asang abnormality there is. So there are a lot, and usually it is through